So here's the story. This is a low-speed aluminum wheel that's already been repaired once. The customer took it to a shop to straighten the rim, and I guess they got it straight enough that it seals. And they've had to put a weld in it, and now it's cracked right through the weld. And according to the customer, that's exactly where it's leaking. So our goal today isn't to repair a high-speed wheel going down the road. That's not what we're doing. This is actually just used on a vehicle that pulls trailers around the shop and around the yard. So it's not going to be going at high speed, just needs to hold air. And the customer just asked if we could fix the weld, nothing more, nothing less, and stop the leak. So that's what we're trying to do. So here's that crack right there, right through the bead seal. You can see it definitely has opened up. And to me, that's a classic sign of either a solidification crack that occurred during welding, because that's how aluminum fails and that's how it's going to crack, or it's possible that they also didn't drill out the end of the crack initially and it allowed that crack to propagate again back to that weakest spot. So let's recap why that initial weld repair might have failed again in the first place. First, in any type of a structure like this or an assembly, you're going to have residual stresses. If they tried to straighten this rim, that did things through cold working to the aluminum base metal that's going to lock in some stress. So that's one thing that we have to think about. The next thing that we have to consider is aluminum is highly crack sensitive. Very few alloys can actually be autogenously welded without filler metal because it requires the right amount of dilution between the base metal and the filler metal so that the weld doesn't crack immediately after it's put in. That's called hot cracking, solidification cracking, centerline cracking, and that's what we see as aluminum fails. So it's possible that they used maybe the wrong filler alloy, and that takes me into welding procedures and practices. Maybe they didn't clean it properly. They didn't get all the way to the bottom of the joint. Maybe they used the wrong filler metal. Maybe they didn't preheat it properly. There's a ton of different reasons why this thing could have failed, and what we're going to do as we work through this repair process to make it stop leaking is we're going to talk about each of those and how the steps that we take in our weld plan address some of the common things that would cause that weld to crack under nominal load. And hey, don't forget, shit happens. So what alloy is this anyway? Unless it's stamped on the inside somewhere, we're just guessing. But thankfully, I found out that rims are typically made from two different alloys. One is the alloy A356, which is a cast alloy, readily weldable. So then the other potential alloy that it could be is a 6000 series, like a 6061, just depending on whether this was cast or forged or machined out, right? I don't think we're in that category right now. But if it were, the cool thing is ER 4043, filler metal 4043, is commonly recommended for both 3000 or 300, being the cast series, and the 6000 series alloys. So we're going to use 4043 because it has the least crack sensitivity of the two filler metals I have right now in stock. The other is 5356, and to be honest, I've used that before for similar off-road applications, and it's worked just fine. But because this is cracked already, may have some residual stress in there, we're going to go ahead and use ER 4043, which is an aluminum silicon alloy, to give us good wetting action, good puddle fluidity, and the least amount of crack sensitivity. So that's how we're going to start out with things going in our favor. In addition, as we prep this thing, we're going to remove all the paint on both sides of the wheel here. And then we're going to find the end of the crack. We're going to drill a hole in it so it can't propagate. And then we're going to go ahead and chase this crack right down from the outside of the edge of the rim here all the way through to the hole that we drilled, so that we've got a nice thin slice to fill back in completely with filler metal. And what we're trying to achieve here is good penetration all the way through, right, with the potential to come through on the back side so that we've got good overlapping penetration in the center of the weld and nowhere for that crack to restart again. That's our goal. Let's see if we can pull it off. So I've got this thing outside so I can see exactly what I'm looking at for that crack. I don't want anything hiding on me. And come on, take a look at this. So I don't know if this is common practice or not, but it looks like what they tried to do is put a weld right across here. I'm seeing some fish eyes in there, lack of fusion and complete fusion at the toes of the weld. That leads me to question the weld integrity from how the weld was put in there, right? That this probably was doomed for failure. So now we can see the crack going right back to probably where it started. So what we're going to do is we're going to find that end of that crack. We're going to drill an 1/8 inch hole in it. And then we're going to go up here and we're going to eat right through that crack all the way back down to the hole that we drilled. And that way we can put that all back together. We can fill that groove with filler metal and end up with a weld that won't crack when we're done. Now, I've seen a lot of things in my day, but I've never quite seen this. You ever seen anything like that? So on the inside of the wheel, this is what the crack's looking like, coming all the way down. And I can tell you right now because it's in and past the weld on the inside that, yeah, we're gonna be chasing some cracks. Nope, there's another ding in this thing too where it looks like you got egged just a little bit. Now you might be asking yourself, why go to the trouble to weld this thing? Well, first of all, if we can stop the leak, it's gonna be good enough for what it's for. And second, they don't make these anymore, so matching this up's kind of hard to do, and what would customers think? So, to chase that crack right on down into here, I'm gonna avoid using any type of massive abrasive right now to remove that paint because it might smear the aluminum. And if you smear the surface of the aluminum, it's really likely that you're gonna miss where that crack ends. So we're gonna be as delicate as we can here to make sure that we don't do that while we're just getting it cleaned up to find the best spot to drill. It just so happens I got a little bit of Scotch-Brite here, which is a relatively non-aggressive, that we should be able to just remove some of that paint and kind of see where that crack actually stops so we can put our hole in the exact right location. Otherwise, there's a really good chance it's going to crack right there again, right? That holds true with cast aluminum, cast iron, cast steel, and some of the white metal castings that I've worked with over the years. All right. This is doing just what we want. I'm able to see right down in here, and I didn't smear any of the aluminum and hide any of that crack. So, light abrasives when you're crack hunting. It also helps if you've got a little penetrant. You can spray some penetrant developer on there, let it sit for a minute, and you'll see exactly where that crack ends. We cleaned off some of that paint, and we're able to see that that crack really doesn't continue much past my fingertip there. So that's the part we're going to aim for. I'm going to go ahead and get a center punch. We're going to knock a punch mark there and use that to drill our hole. Nice. That'll keep that drill bit from walking around. Now the cool thing is, on the top side of the hole here, I can actually see where the crack comes right into the hole that I drilled. On the rest of the hole, I don't see a crack going anywhere past it, so that tells me we got to the end of the crack. And we're ready to move on to the next phase. Cross your fingers that this goes well. Oh. Okay, so before we get out the mechanical abrasives, aka the grinder with the right aluminum pads on it, I'm going to see what we can do just cleaning this up by hand, continuing to use the Scotch-Brite and my handy dandy stainless steel toothbrush. So let's give it a good brush back and forth here. Oh yeah, it's shining up nice. When you're cleaning aluminum, you want to use a dedicated stainless steel brush to avoid cross-contamination. Don't hit this with a regular carbon steel wire brush and think that it's going to weld clean, because it won't. Ask me how I know. Yeah, I've tried it. And it is eating off the paint on the top side here as well. So let's just kind of keep going. As it's coming up pretty good and flaking off, I'm going to go ahead and get my respirator, make sure that I'm not inhaling any of this paint that contains who knows what, right? Now we got a suitable amount of PPE. I'm trying to keep this aluminum off my hands. I don't want to absorb any of the aluminum and certainly not any of the paint particulate here. So we're outdoors, we're in a well-ventilated environment, And we're going to try to keep that stuff going away from us. There we go. All right, so this is kind of formulating my next plan of attack. What I was able to do is get through some of that heavy paint. And if you come on up and take a look right here, you're going to see what I'm talking about. This initial weld was sus. I can see fish eyes and craters right in the weld. Yeah, you see that? That's not good either. Because any place we've got a crater that's unfilled, there's a potential for cracking to occur. Because an underfilled crater places the crater in tension, and a filled crater puts the crater in compression. And most things are stronger in compression than they are in tension. So this makes me think we got to hog as much of that weld off that we can and get back to some relatively undisturbed base metal underneath of it. So we're going to be breaking out the power tools now. I'm going to go ahead and put my face shield on, and we're going to take that thing down into good metal that we think we can restore. All right, sit tight. What we're going to be using here is this aluminum flapper wheel, and it's not brand new. I've used it before, but they are approved for use with aluminum materials. It's best not to use one for steel. They're going to load up and wear out a lot quicker. So we're going to use this one because this is pretty dirty. I'm going to go ahead and use one that is used, but not used up. Well, full PPE. Let's see how long it takes for this lens to fog right up. Woo! All right, this is a classic example that more weld doesn't make it stronger, right? Piling poop on poop just makes it more poop. All right, so as with any project, it's the cleaning and the prep, especially on a repair like this. There's dirt, debris, there's grease, there's oil. So probably the next best thing, or the next thing we ought to do as we move forward after grinding and prepping the joint, cutting down there to our pilot hole, is to go ahead and use a degreaser on it, right? And that's something that you're going to want to look into. My favorite degreaser is Dawn dish soap. If it's safe enough for animals and oil spills, it's safe enough for me. Just don't tell the boss that's where all the Dawn dish soap is going. All right, we got to get down in there just a little bit more, right down into there. And what I'm trying to do is not take too much wall thickness off anywhere that wasn't welded, right? So we're going down to the original base metal, and I'm being a little bit cautious because I'm going to eat right through that weld. You may be tempted to just cover that weld up with weld, right? To just cover that crack up with weld. Don't be tempted to do that because it's going to crack right in the same exact spot. If you don't remove the crack, it's only a matter of time before it propagates back through the new weld. What I'm seeing along in here, this is the original weld that they welded transverse to the crack, right, at 90 degrees across there. I was trying to get into that just a little bit. That's actually the toe of the weld, even though it looks like a crack. That's where it didn't really blend in with the base metal. I was looking to see if this weld had cracked, right, and maybe that's why they chased it, or did they think that by welding across it, it would stop the crack? Well, that's not the case. We've got to eat the crack out, put new weld metal in here, and then we don't need to weld across there, right? That's not going to do anything for us. So unless I find something more when I'm opening up this can of worms, I think we're going down the right path. We just need a new flapper disc for aluminum. And here's the reason I'm running my respirator, right, and I'm wearing my mask today, is because I haven't always done that in the past. And look at all those aluminum shavings that are coming off that process. So you're going to want to protect yourself from this aluminum. It is not good to ingest, right? We know what it's linked to as we age. So practice good safety, protect your health out there. We're back with a new flapper. Let's see if it finishes it up for us. Well, okay. Looks pretty clean, looks pretty smooth. I'm not seeing any new cracks jump out at me. That's a good thing. Oh, and hey, note to self, if I don't set this down when I'm done on the concrete, the face shield's going to stay clear a lot longer. I just got to get that through my head. Okie dokie. We got a little more cleanup to do, but we're not far from it. All right, by now we're committed, so we get to do the fun part. We get to chase the crack, and I'm going to do that real carefully here with a Sawzall blade. It's going to give us a pretty narrow curve if I can hold it. Whoops. There we go. Right on down through that crack all the way to our start-stop hole. Perfect. Okay. So let's recap. We've got this off-road rim here that's going to be used for non-highway speeds. It was already repaired once. It was brought to us with a crack right down the center line of the weld. So what we had to do is a little bit of inspection. We found the end of the crack. We drilled it out with a hole about 1/8 of an inch in diameter. And then I used the Sawzall to cut right down the crack to that hole. That way the crack is not there anymore. Or you may say, I just made it worse, right? So we've cleaned it off. We're at the stage now where you may be considering some preheat to burn some of that crud out of there and to get the puddle to flow a little bit easier. So let's talk about preheating aluminum. So aluminum's not like steel. Steel we can pretty much heat up to a few hundred degrees and not have to worry about anything happening until you get to that critical temperature above 1,000 degrees, right? Or somewhere in that ballpark. But aluminum melts at about 1,000 degrees. So it's a whole different animal. At the same time, hardenable alloys go through a process called aging or artificial aging, where they're heated to about 400 degrees and held there for a period of time. And to a certain point, that increases strength. But after a period of time, it actually causes it to get weaker. It's called overaging. So we don't want to heat the aluminum up anywhere near that potential. At the same time, it's going to be cold worked. And sometimes those materials undergo strain hardening. So the higher we heat the base metal, the more chance we're going to anneal any of that cold working. And I'm not so sure we want to do that in this case, right? Because we're deriving strength from the way this thing is shaped and formed. That's my take on preheating aluminum and the dangers of it. That's why most manufacturers only recommend you preheat to about 250 degrees, 300 degrees maximum if you really know what you're doing. But at that point, it's really easy to overheat it and get into that annealing or overaging condition, which can weaken the aluminum. So again, what we're trying to do is burn out the grease and the moisture. And if we get just a little over 200 degrees Fahrenheit or 100 degrees Celsius, we're going to accomplish that goal. So there's no reason to get it any hotter than that. Right on? Now let's look at some ways to preheat. And sure, you might be thinking oxy-fuel is a great way to preheat, and it's a good option. However, you should know that the byproduct of that flame burning is water, good old H2O. And what do we want to keep away from aluminum? Moisture, because moisture, one, has oxygen with it, right? And it can oxide our material. And two, hydrogen in aluminum is highly soluble in the puddle. That means that those little bubbles get absorbed into your puddle while it's liquid, and immediately upon solidification, that hydrogen is rejected from the puddle because it's not soluble anymore. It causes gas bubbles, and if your puddle solidifies too quickly, you're going to have porosity all the way through it. We call that the Swiss cheese weld. So after all that, I'm going to do something different. I'm not going to preheat it, and I'm not going to degrease it. I've got it cleaned up pretty good. I cut right down through the center of that weld, got rid of all the trashy material around it, and what I'm going to do is I'm going to use the arc cleaning action of the Lincoln Square Wave 205, set with the balance just a little bit lower than I'd like to run, and let that clean and eat through the oxide. And if I see that it's pulling a ton of trash out, I'm going to stop and I'm going to continue with my cleaning process. But there's no point in taking this down to aircraft quality cleanliness if it's going to weld just fine with a little bit of lower balance setting. What do you say? Let's take a look. So here's a tip if you're looking at aluminum and you don't know what alloy it is. I typically have two alloys in my shop, 4043 and 5356, and I can tell them apart easily just by doing a simple bend test. Watch this. If I take this 4043 and I bend it, it kinks right where I bent it. You see that sharp kink? Now, if I take this piece of filler rod and I bend it, it wants to curve around my thumb. That's 5356. And that's a good way to tell what filler you're holding on to in your hand. All right, let's set up for welding aluminum today. In this case, I'm running 100% argon shielding gas. You could mix a little helium with it. Helium increases the arc voltage at the same output current. So by doing so, it increases the arc energy, and it actually can help aluminum melt just a little bit quicker. Helium also slows the cooling rate, so welds made with helium are less likely to have porosity. Okay, let's take a look at our Lincoln Square Wave 205. We've got to set this up a little differently. So, nope, wrong button. We'll go back here and we'll do our process selection. All right, we're going to be in AC TIG mode. We are running on 230-volt primary input, so we can get maximum output out of the machine, which is 205 amps. Okay, let's take a look. My pulsar is off. My balance is around 70%, and a lot of times modern machines are coming out up at about 75, so we're going to back that down. I'm actually going to go to 68% electrode negative, which is the maximum that older technology, like the older square wave transformers and the older synchro-wave machines, that was the maximum electrode negative you could get. All right, AC frequency, I like 120 hertz. Post flow, automatic. So it's going to give us 1 second for every 10 amps we're welding. That way we don't waste gas and we don't weld too hot and smoke our tungsten. Okay, let's click the back button. We're ready to weld. I'm going to put my work clamp as close as I can to the weld joint, right? So that current doesn't have to travel very far. At the same time, I don't want to attach through paint or any corroded surfaces because chances are it's going to arc through that paint because it's not a good conductor. Oxides are also not good conductors. So try to find some bright metal, even if it's a little bit away from the weld joint, and make sure that you're connecting your work connection to good bright metal so you have good contact. Do not ground to your table, connect your work clamp to your table, and lay this thing down on the table because it will arc mark everywhere that it tries to find a path, right? I've seen it happen before, and it can ruin a relatively simple repair job. We're using the Fusion Grip TIG torch with the blank insert because we're running a foot pedal today. And one of the things I like to do when I first fire everything up, because I had everything depressurized, is go ahead and bump that foot pedal to get that gas flowing so we get a little bit of purge through our hoses before we try to strike an arc. Well, it definitely pulled some trash. You can see the speckles, the black pepper in the puddle. That definitely was trash pulling out of that joint. So we made the best of it. I let it eat in there, and we got a decent looking bead on that side. However, we are not done, because as you can see here, we did not penetrate all the way through the joint, which is fine. We're just going to have to go in here and back grind this until we see bright metal on the other side, and then we can get our weld to go in it. We'll overlap and not have any more leaks coming from this spot. On a weld like this, where we didn't shield the backside from oxidation, you can bet that down inside that groove, we've got a heavy, thick oxide layer on the backside of that weld. So what we've got to do at a minimum is open this up a little bit so that we can get down in there, get it into bright metal. We'll re-clean it with our stainless toothbrush, and then we'll go ahead and put our back pass on here and seal this thing up. All right. Always best to weld in the flat position and have gravity work for you. I'm going to weld this in the vertical up position right now because we're tipped slightly uphill. And it's going to do a couple of things. One, it's going to let me get a better camera angle, I think. And two, what I'm going to do is I'm going to be putting more heat into the material as I go vertical up, and that heat's going to rise ahead of me and preheat that aluminum as I get to it so I can be sure to penetrate in and overlap with the weld that I put in from the other side. Let's take a look and see if it works. All right, and that was just a cleaning pass, just running with no filler, letting it eat and etch out next to the weld right there. As I started to weld up here, everything was going really good, and then I hit this corner and split. I had some crud come out at me. So we're going to have to doctor that one up again. That's just one of the things you run into on a repair like this. Okay, we rolled this thing over into the flat position, and like I say, what I've got to do is clean this up, get it all welded up to the corner. Then I'm probably going to do a little bit of sanding and a little bit of touch-up cleanup, because cast aluminum is notoriously porous. So it's gonna off-gas on you the more that you melt it. So what we have to do is kind of take it one step at a time, right? Cross your fingers, hope and a prayer, never hurts. All right, let it eat a little trash out of there. Re-clean it with our aluminum toothbrush here. Yeah, so there was definitely some trash down in there right now. I didn't like the way that that looked as soon as I hit this curve. And, yeah, we're going to have to clean it and keep chasing after it now. Yeah, so if you see down in here, that weld was going really good, really smooth. And as we got toward this corner, swoop, it went to shit and started to pull trash out of the inside of that joint. So yeah, we're going to clean it back up, and we're going to sand her down and go at it again. Upon further inspection, I'm convinced this is probably an A356, right? I'm convinced it's probably. Did you hear that? But it's definitely a casting, and one of the things that is a clue upon further inspection here, right, is I'm critiquing my own weld as I'm sanding it off. I'm looking at the inherent porosity in this casting. So expect when you weld on cast aluminum for it to bubble up at you. It's just its way of showing some love. Okay, so here's where we're at on this side. what I did, I kind of had a little nick right there from the abrasive wheel. So we're going to go ahead and cover that up so that we can blend this all smooth. And you can see some little areas of porosity that we had. So our mission on this goal, because the last one we tried to fuse all the way down in there, get a good sound weld. I saw no evidence of cracks on the inside or the out. And as you can see, we're at room temperature. Aluminum does solidification cracking or hot cracking. So chances are, if the crack's not showing up right now, it wasn't caused by welding this time. So what we're going to end up doing is just putting a nice cover pass on here that we can blend back down, and hopefully we won't continue to see those pores. The less pores, the less likely that it's going to leak again. All right, and once we're done with the inside, I probably will come back and we'll sand this down and we'll put a nice cap pass on that. That way we've got a little bit more confidence that when they mount the tire back on here, it's not going to leak, and definitely it's not going to crack.
So that's it, the textbook repair. I drilled the crack, opened it up, cleaned what I could, welded it back together. But I'll be honest, I saw a lot of trash on the way. Oxides, inclusions, contamination, porosity. The stuff you don't want to see in a wheel that's already been welded once. And remember, this was already a botched repair. When you skip steps, take shortcuts, weld over someone else's mistakes, things have a way of coming back to bite you. I've got concerns. I got a lot of questions that I'll probably never find answers to. And I've got a feeling this story isn't over. What do you think? Did this wheel crack again? What do you think I found after the repair? Tune in to part 2 for the conclusion as we take a deeper dive into the world of wheel welding. Thanks for watching, and until next time, keep your hood down and don't stare at the bright lights.